E aí pessoal, tudo bem? Como estão? Gostando da RBCC? Bom, a RBCC tá um evento top, em virtual, palestra boa, tema importante. Tá de parabéns, comissão organizadora, show de bola. E aí pessoal, tudo bem?
Peixoto, I think you can start.
Boa tarde a todos. Hoje estaremos iniciando mais um seminário da Reunião Brasileira de Citogenética e Citogenômica. Esse seminário de hoje é um seminário conjunto com a participação da equipe do Instituto Nacional de Tecnologias Alternativas para Detecção, Avaliação Toxicológica e Remoção de Contaminantes Emergentes e Radioativos, o DANTREM. O objetivo do seminário é estreitar os laços entre os pesquisadores brasileiros e internacionais que utilizam metodologias citogenéticas e citogenômicas nas mais diversas frentes de pesquisa. Hoje teremos uma palestra com o Dr. Stefan Pfuhler, Validation of the 3D Human Skin-Based Micronucleous Assay. Para nos assistir e moderar essa apresentação, teremos a participação da doutora Daniela Moraes Leme, da Universidade Federal do Paraná, que é doutora em Biologia Celular e Molecular pela Unesp de Rio Claro, professora do Departamento de Genética da Universidade Federal do Paraná, coordenando o Laboratório de Ecotoxicologia in vitro associado ao RENAM. Ela também integra a rede da equipe do INCT DANTREM. Também participam com a gente como moderador o professor Dr. Daniel Junqueira Dorta, doutor em toxicologia pela USP e professor de toxicologia e química clínica no Departamento de Química também da USP, presidente da Sociedade Brasileira de Ciências Forense e também membro que integra a rede do INCT DANTREM. E dando apoio, dando suporte para essa apresentação, estarei também presente. Eu sou o Aparecido Divino da Cruz, todos me conhecem mais pelo nome de Peixoto, que é meu apelido e eu prefiro. Sou doutor em Biologia Molecular pela Universidade de Vitória, da British Columbia, no Canadá, professor titular aqui da PUC Goiás, coordeno um núcleo de pesquisas em genética da universidade chamado Replicon e sou participante e organizador da atual RBCC. Sejam todos bem-vindos, agradecemos pela presença em nosso canal do YouTube e passamos então a presidência dessa tarefa desse webinar para a doutora Daniela. Obrigado.
Thank you, Peixoto. So, it's a pleasure to introduce Dr. Stefan Pfuhler because I have been following his work for years. So Dr. Stefan Pfuhler has a Master of Science in Biology and developed his PhD thesis in the area of pharmacology and toxicology. He is a research fellow in the Global Product Division of the Procter Gamble company. He leads the company's genotoxicity expert team and develops and executes their genotoxicity research program. He manages product and ingredient issues related to genetic toxicology and develop and support in test strategies and policies across the entire company. Also, he is a member of the OECD Endpoint Expert Working Group on Genotoxicity Guideline Revision, as well as OECD Expert Working Group on the genotoxicity of nanomaterials, and is involved in several other professional activities and membership. So thank you once again, Dr. Stefan, and it's an honor for us to have you here today, and the floor is yours.
Thank you very much for your kind introduction, and certainly an honor and a pleasure for me to present to this group. And let me try to share my screen.
Okay.
It worked before, so I hope it'll
It's uploading now. Is it starting? Yes. Yeah, it's
so,
okay.
Yeah. And now
The presenter mode.
presentation mode. Hopefully that will work. So
Yeah.
you can see the slides, okay?
Yes, it's fine. Thank you.
Okay, perfect.
Just click on hide,
Excuse me?
and you can just click on hide, and you're going to disappear this bar.
Well, I don't see that when I share my screen. I mean, okay, hide. Okay, now I got it. Thank you. All right, I just today I want to use the opportunity to talk about reconstructed human skin models and how they can be used in the field of genotoxicity, and just maybe to give you a little bit of a glimpse on that journey that we have been taking. Really, I think the work was triggered by some regulatory change that came our way with the 7th Amendment of the European Union Cosmetics Directive, when testing of cosmetic ingredients was banned in 2009. And really, that forces in vitro only testing concepts. And I mean, it's not only that, of course, also for us, it was a great opportunity to think about this, because nobody really likes in vivo testing, and it's not a concept that's going to, I think, be sustainable in the long run. So the challenge that we had was that I mean, the classical in vitro battery that, I think, contrary to some other areas in gene tox, is accepted for a long time. It's known to be sensitive, but it produces also some misleading or false positive results. And that is probably because, I mean, when these assays were generated, then of course the focus was on sensitivity, on the correct prediction of carcinogens, and be it rodent carcinogens, and not necessarily on the correct prediction of non-carcinogens. So that was a bit of a problem for us, and that is what kind of triggered the start of the cosmetic syrup strategy, which we started working on, I mean, by now 15 years ago in 2006. And I mean, that was not only the skin models, it went a bit beyond that, but I mean, I'll focus on the skin for today. I mean, the idea was to have a exposure-specific approach in place to work on that. And of course, for cosmetic ingredients, the main route of exposure really is the dermal route. And I mean, that's why the focus, especially the initial focus, was the reconstructed skin models. And we chose two kind of readout parameters, if you will. I mean, the COMET assay and the micronucleus assay, I explain a little bit why that is. But then also have a program or support a program that's looking at other routes of exposure that lead to higher systemic availability. And that is the HENSEC micronucleus test. And I'm not going to talk about this today, but I left one slide in my slide set just that explains a little bit how it works, hopefully triggering some interest in case you have not heard about that assay. And that is actually currently undergoing validation as well. The respective manuscripts actually just have come out. So in case you wanna look for that, for this assay. Now, for us, very importantly, it was clear to us that this is something we can't do in isolation, right? I mean, not just as industry, and obviously also not just as one country. So we were trying to get feedback on these methods and scientific input in various international scientific meetings. And I mean, they're all listed on the slide. I don't think there's a need to go through them, but I wanted to highlight the international workshop on genotoxicity testing in Japan. I mean, there was the one after that only takes place every 4 years. The one before was in Iguazu in Brazil, and I really enjoyed that one. And in Tokyo, we had a work group that looked at these models, and that helped us kind of to get to a more clear agreement in where we stand. And that led to also to the OECD guideline proposal for both assays, for the micronucleus and the COMET assay based on the skin models. And both were actually accepted into the OECD work process in 2019. It's also has been accepted into the European Center for Validation of Animal Alternatives. It has been accepted there for the peer review, and I'll say a little bit about that at the end, I think, if there's time. Now, just wanted to, instead of kind of presenting bullets that I have developed, I wanted to show you the consensus statements of that international workshop in Japan based on the 3D tissues. And I mean, so the consensus of all the people that were on that work group, which is from different geographies, from academia, industry, and regulatory agencies, agreed that the 3D tissue-based assays can be used as a second-tier assay to follow up on positive results from standard assays. The 3D assays are obviously based on human tissues, right? So different from the animal experiments you're doing. And they certainly allow for more specific exposure investigation, as is, I think, very obvious for skin. They also offer more in vivo-like behavior for a lot of the key parameters we are interested in, and therefore they're a valuable complement to the classical 2D assays. And I mean, there was a lot of discussion about the endpoints that need to be looked at, and there was agreement that there is important that for each tissue models, the full range of genotoxic damage leading to mutagenicity, elasticity, and anagenicity can be detected. And that certainly leads into the selection of the COMET and micronucleus assays. So again, of course, if we want the assays to serve us in the context of following up on positive results from the standard in vitro battery, then the micronucleus would be an obvious choice to do that for a compound that causes classigenicity or anagenicity in a micronucleus or maybe a chromosomal aberration classical in vitro study. But it's not so obvious a good tool for a positive in, let's say, an Ames assay or a mammalian cell gene mutation assay like an HPRT or mass lymphoma. So now, but there was agreement that the COMET can detect substances that induce DNA damage that is leading to gene mutation and chromosomal damage. And of course, the RSMN, I think more obvious, detects damage that leads to plastogenicity and anagenicity. So that kind of explains a bit the concept and why we have more than one assay. And now how do we use that strategically? And I think for that, I need to introduce the two-test battery, what we call the two-test in vitro battery, because different geographies and different regulatory jurisdictions use different concepts how to test for genotoxicity. I think it has been shown in the last 10 years or so that I mean, what you need to detect everything in that range is basically an assay that detects mutagenicity and an assay that it detects anagenicity and clastogenicity. So, and it has been shown that a two-test battery consisting of the Ames and the micronucleus in vitro really does a very good job in identifying the in vivo positive agents in that space. So now that's how this would look like. I mean, if you run an Ames and that's negative, we run a micronucleus in vitro. If that's negative as well, then in the context of cosmetics, where there's no regulatory need to do in vivo testing, we would think that no follow-up is required. If the Ames is negative, micronucleus is positive, then we would test in the reconstructed skin micronucleus. If the Ames is positive, micronucleus is negative, we would test in the COMET. If both were positive, then we would have to test in both models. And but I mean, as you can see from the asterisks here, I mean, in the real world, in at least in industry, I mean, if you have a double positive from the standard battery, you wouldn't normally touch that compound any further. So that's not a typical scenario in R&D. Now, I think another important element when it comes to these assays is a bit of knowledge what the skin models are capable of doing and maybe what not. And of course, the first thing that comes to mind is the barrier function, and I don't have a slide on that, but I think it's fairly obvious that the 3D skin models also have a barrier function that's quite different from a standard culture, cell culture, where you expose the cells directly, while on a 3D model, you're exposing the cells from the top, from the stratum corneum on the skin. So you basically have this penetration barrier before your test material gets to the living cells. We've had a program that looks into metabolic competency in the skin models, and this is just a bit of an illustration that shows you that actually, I mean, the skin can actually do quite a bit in the space of metabolism. But of course, when you look at the relative size of the the relative size of the arrows that are depicted here, of course, the liver has a higher capacity, but the skin can do a lot of things, and it actually can also do something missing here. But I mean, where the arrow is pointing, actually, that's supposed to say hydroxylation. I mean, the CYP450 hydroxylation reactions are not present in the skin typically, but they can be induced. And that's what typically happens. I mean, if our skin gets exposed to an item that needs to get detoxified by hydroxylation first, then the skin actually can produce these enzymes, and that's happening, and we've shown that as well. There's also an effort that was also sponsored by Cosmetic Syrup in the context of using human liver and skin S9 fractions as a screening assay to compare hepatic and dermal metabolism. And that might be interesting for folks that are interested in that topic. I'll come to back to that later too for a different reason towards later when I'm presenting a case study. Now, how did we approach the validation of these models? I mean, obviously the initial step was developing the method, but then of course there's quite a lot of work required before you can convince OECD that a method is worthy of a guideline. So the way we did that is we had an international team that actually involved the alternative methods expert from ECVAM right from the start. And then we did the substance selection via some substance matter experts. So we invited external experts to help us select the right chemicals for that effort, and put together a steering team and as needed for the decisions we had ahead of us. And we had a total of 6 labs in experience in gene tox testing involved in this, and we're in constant discussion and calibration with the scientific community over this. And for us, the Scientific Committee of Consumer Safety of the European Union that does really look at the safety of cosmetic ingredients, that was, of course, an important partner in this. And we got encouragement for them along the way. And already 2014, they have mentioned these methods as a valuable additional method in their notes of guidance. And the last notes of guidance really lists it as a formal tool in the toolbox to assess the genotoxicity potential of an ingredient. Now, the project itself, the validation was set up in 3 phases. The first phase is optimization of the protocols and transferability, done with 2 model genotoxins. And then we did a inter and intra-lab reproducibility with a larger number of compounds. And then at the end of the day, a validation with 30 plus compounds per model. And again, the chemicals were selected by international experts. It was all coded and was handled through ECVAM, from like a regulatory, if you will, agency, and others helped coding and shipping the chemicals. The decoding was done by ECVAM again, and the independent analysis was done by Sebastian Hoffmann and a statistician from the German Federal Institute for Risk Assessment. Like the data actually was just published earlier this year in a special issue that I co-edited together with Raffaella Covi from ECVAM. It contains 5 manuscripts, including these fairly lengthy validation papers. In case you're interested, that's where you find them. The validation of the COMET and micronucleous assays. And with that, I want to give you just a brief glimpse on the protocols. I mean, we don't have time to go into detail for everything. But I mean, what you see right away is for the COMET and the micronucleus assay, there's different tissues used. For the COMET assay, we're using full thickness tissues that consist of a dermis and an epidermis. And in the more simpler epidermal model, the MATEC epiderm, basically the dermis is replaced by a carrier membrane. So, but that model only consists of keratinocytes. The COMET assay, the Phenia model consists of fibroblasts and keratinocytes. And I mean, we are treating topically. I'm not going to go through the details of the protocol. Isolate the fibroblasts and keratinocytes separately and analyze them for COMET for DNA damage in the COMET assay, measuring TNA, percent tail DNA. And really, I mean, basically do solubility study, a dose range finder, and then main experiments, and at least 3 concentrations of the test chemical. This study for the COMET assay actually also includes a protocol of acetylcholine, and that's a DNA repair inhibitor, and that's actually involved in the in 4 hours before the end of the treatment, which helped us to increase the sensitivity of this assay. So, but that's only for a COMET assay. For the micronucleus, protocol is quite similar. I mean, other than obviously the details are different because you have a different type of preparation at the end. And we are looking at this in the context of, a classical microscopical scoring and a look at micronuclei. Really, I think initially in the study, we had a 48-hour protocol, which means 2 dosings at a 24-hour interval. So we were dosing at 0 and 24 hours, then did the cell isolation at 48 hours, and later find out that a three-dose protocol is probably more sensitive, and we're kind of moving towards that as the confirmatory assay. So, and I left that picture in for the HENSEC micronucleus just to show you that you can run a micronucleus assay in fertilized HENSECs at a stage where the embryo has no nerve system developed, and they are technically not considered animals yet. And that study actually is also showing quite a high predictive capacity of this assay, and the validation papers are actually already online, I believe, just very recently, also in mutagenetics, in a special issue on skin tissues, and not skin tissues in this case, all 3D. So it has some data for 3D, the HENSEC test, some for liver, 3D liver, but also some data actually for bone marrow models. Now, the outcome of the validation, that's kind of what you're looking at the end of the day. The 3D skin COMET assay, we've tested 32 chemicals. In the 3D skin micronucleus, we've tested 43 chemicals. The sensitivity of the COMET is 77%. And actually that is by expert call. What you see in brackets is the outcome when the prediction models of the statisticians was used. And the specificity is 88 or 97%, overall accuracy, above 80 or 90%. For the RSMN, sensitivity is 75%, specificity 84, and accuracy 80%, which are really good numbers. I think sometimes the difficulty is that people compare the numbers and set different bars for in vitro assays than they would set for in vivo assays. And I think if you look at the numbers for in vivo assays that have ever undergone formal validation, I think they would be lucky to see something like that. Now, the chemicals tested do overlap, because if a substance had a positive in the AIMS and a positive in the micronucleus, which actually most of the real positives, most of the rodent carcinogens actually had, then they would have to be tested in both assays. And when you do that, the overall sensitivity increases to 89%, and the overall specificities decreases slightly to 79% when you do that. But the specificity is still much higher than when you look at the ability of the standard test battery in vitro to correctly detect a non-carcinogen, because that often is actually below 50%. And again, everything is in the context of this strategy that I had just mentioned. And by the way, it's fine to interrupt me in case there's any questions as I'm speaking. That's totally okay for me. Now, I'm going to walk you through what the validation results look like, just giving some example, because we won't have time to go through everything, right? Because that's a huge data set. So now when you look at a selection of what the external experts designated as true negatives, you can see, from the setup, how this worked, right? Some were tested in one lab only, some were tested in 2 or 3 labs. And that's really dependent on when they were picked, at what status validation. And now when you look at this, I mean, you can see that some are very clear. I mean, for example, I mean, most of them were correctly predicted at negative, and then some are incorrect across the board, like diclofenac was, for example, positive across the board in all the labs fairly clearly. So that's an incorrect result, but it's reproducible across the labs. And then you have situations where some labs detected it correctly, but other labs didn't. And then, I mean, the final result that goes into the calculation of the predictive capacity, I mean, in this case, 3 out of 4 labs predicted it correctly, so it was correctly predicted by at a level of 75%. So that's the number that would go into the calculation of the predictive capacity. Now, yeah, and I mean, for phenanthrene, even we had an explanation because it was actually precipitating fairly strongly, and that was not something we had initially controlled for. And I mean, when that was controlled for, actually, the result was I think, favorable. So we could have overturned that, but we didn't want to bias the cause here. Now, when you look at negatives, and again, this is now already a table that shows you the result from both. And when you see RSMN and you see 2 of 2, then you know it has been tested in 2 labs and was correctly predicted in both labs. When you see, like here for phenanthrene, and I don't know if you can see my cursor, if you see a 3 out of 4, that means, I mean, as I had just said, I mean, it was correctly predicted in 3 labs, but not the 4th. And diclofenac, you see, again, it's incorrectly predicted in the RSMN, but was actually not tested in the skin comet, so we don't know how it would have done there. Now, when you look at the false positives, again, you can look at, and these are actually false positives. To explain that, these are chemicals that actually were positive in the standard test battery, but actually that are negative in vivo. There's in vivo data showing they are negative. And then we look at that picture again, how the skin assays were doing, and then you find then situations where both agree, but then you also find situations where they disagree. And for example, in curcumin is, as you all know, a natural component that actually tests positive in, I would say, almost all standard in vitro gene tox assays. It tested negative in the skin comet, but it tested positive in the skin micronucleus. So that still counts as an incorrect prediction overall, because we have tested it in both assays, and if one picks it up, then it's going to go to red for the whole thing. And that's an explanation why the specificity is going down, right, when you combine assays. And I mean, for resorcinol here, you can see for the micronucleus, it was kind of inconclusive. For the comet, it didn't pick it up. No, it picked it up as positive. So again, that one would go in as a false positive call. Now, when you do the same thing for all the true positives, then in this case, the positive calls in a way multiply, right? So in the context of, for example, DMBA or 2-aminoanthracene, you can see they were not picked up in the RSMN, but actually they were picked up correctly in the COMET assay. So one of the assay would flag them correctly as positive, and they were actually positive in the Ames and the micronucleus, then they would still get flagged as a potential in vivo positive. So that is a correct prediction. But of course, for example, down here for parachloroaniline, there's only one assay done, and that was positive. That was actually negative, sorry. So it's an incorrect call, and that would go in as an incorrect prediction. And when you do that with that set, you get to an overall sensitivity of 89% for the combined approach of COMET and micronucleus. Let me pause here just for a second just to see if there's any questions in relation to the validation before I come to the case examples. Just in case somebody has any questions there. I just want to make sure I'm not losing people.
I guess so far we don't have questions.
Okay. Perfect. That's fine. And of course, we can come back to these things at the end as well.
Okay.
So now, when you use these models in practice, what we have seen so far, at least, is that this is confirming an excellent specificity. And there's a data set here by RIFM, which is the Research Institute for Fragrance Ingredients. And we've just summarized the data in a paper that has been submitted to mutagenesis, and it's part of their screening program for potential gene toxicity potential of over 2,500 fragrance components. And the way that was done, I mean, they had done blue screening to prioritize, and then done the two-test battery aims and micronucleus. And if they were positive in these assays, then they were a skin assay was done. And in the context of that work, quite a few of these actually were also flavor components. So they were used not only dermally, they were also used orally. And therefore, there was a need for doing in vivo testing for those with oral exposure. So that gave us comparability data. But at the end of the day, what we are trying to do in the midterm is avoid in vivo testing overall, and also in the context of oral exposure. And that's where this HENSEC micronucleus test comes in. So that's something we're working on actively as well. This is the data set that will be in the paper that's submitted, if it gets accepted, right? I mean, we don't have any details yet. And you will see 19 pairs of skin micronucleus versus in vivo bone marrow micronucleus data. And actually, the bone marrow micronucleus was done as GLP OECD guideline studies. And I mean, at least for 18 out of 19 of those studies, they are that. And then one, I think, in one case, the data came from a read-across analog. And I think there were a couple of cases where the in vitro micronucleus was kind of borderline, right? So it was positive or equivocal, but most were clear positive. And actually, for all of them, the skin micronucleus was negative, and the in vivo studies were also negative in their context. We have a case that is more kind of, I mean, that doesn't come from necessarily from the Cosmetics Europe program. Some come from that, but some come from Procter Gamble in-house data in the context of when we still had hair dyes in our portfolio. And I mean, it illustrates the importance, obviously, of skin metabolism and penetration barrier. So now, what phenyldiamine might sound familiar. It's an aromatic amine. These are always problematic when it comes to genetic toxicology. And I mean, the data situation from the dossier that has been submitted to the SCCS is that it was pretty much positive in most of the standard battery assays. It was positive in the Ames, was positive in the chromosomal aberration assay. It was positive in the mouse lymphoma assay, although according to the revised criteria, that's probably not going to be a positive anymore. It was negative in HPRT. So it was assessed as non-genotoxic in vivo, since there's comprehensive in vivo data available that shows that it's negative in vivo. And it also was shown to be N-acetylated when applied to human volunteers in hair dye formulation, basically N-acetylated completely and fairly quickly. So we already kind of had an idea what's happening and why it's probably not doing something in vivo. So what we've done internally in Procter & Gamble, we have done a study with PPD in the skin micronucleus assay. And we have done 2 repeat experiments, and they both came out negative, and basically didn't see any thing here. I mean, the line here with the squares is the micronucleus count, and the dotted lines are 2 different cell counts or cytotoxicity parameter. One is binucleation, the other one is cell count. Now, of course, that gives you the idea that there might be kind of a first pass effect when PPD kind of penetrates through the skin. And the skin, as you may know, is proficient in N-acetyl transferase conversions. So what we have done in our lab is we have tested PPD in actually a NAT1 deficient cell line in standard V79 cells, and then tested it as well in V79 that had N-acetyl transferase cloned in, as well as in human keratinocytes, HACAT cells, that also are N-acetylase proficient. So what you see is it's negative in these NAT proficient cells, but clearly positive in the V79 cells. And so it really supports a first pass effect. And now the Cosmetics Europe has done some studies in context with the paper that I showed you earlier in the presentation. It's Eilstein is the first author, and they compared more than 40 compounds when they were metabolized with liver S9 versus skin S9. And what you can see here is that when you do that, and you look at the reduction, and the green lines is kind of where you started, right? You see a very quick reduction of the parent, very quick conversion of the parent, and even, I mean, the skin is actually orange, the liver is pink. So you see that's a bit faster in the liver initially, but actually the skin is catching up. So the skin S9 is actually quite competent in reducing the parent and metabolizing the parent. Now when you look at that, and I mean, you have to know also that it's penetrating at quite low rates into human skin. Now, when you look at the formation of diacetyl PPD, then what you see is that the skin and liver actually are quite similar in that they produce fairly quickly the product of that metabolic pathway, and you can see that after only what is 4 hours here, pretty much everything that was subjected to the skin is converted to diacetylated PPD, which we have shown to be non-genotoxic. So it's just one example I wanted to show how these work. So now let me get to the second example, and that's actually going to come from the nano area. And the slides are courtesy of Professor Doak from Swansea University, and I've worked with them on skin models a bit, and they have been testing nanoparticles with the skin models and compared the data with what they are seeing in standard 2D cultures. And I thought that was quite interesting, because what they are seeing, and now you're looking at micronucleus formation here. The bars are the micronucleus frequency, the lines are cytotoxicity. Gray is the 2D assay, which was done, I think, in TK6 cells, and green and blue and green is the 3D assay, and actually what is blue is submission on top of the tissues, and green, I think, is submission. I mean, you really applied the nanoparticles into the medium. And what you can see is they have a fairly clear increase in the 2D cells, but there's nothing happening in the 3D cells, other than that you are getting a clear positive toxicity effect at that highest dose. And actually, this is how the tissues look from the top. So they are completely covered with nanomaterials and basically get suffocated. So and I'm almost surprised that, I mean, there wasn't an effect, because of course toxicity can lead to DNA strand breaks for sure as well. Now, when they looked at electron microscopic pictures, what they saw is that the TK6 cell really took up these amorphous silica particles quite liberally into the cells. So you can clearly see an exposure. And of course, that will cause some stress to these cells, which might explain the positive response there. But actually, when you do the same with the skin models, and I mean, it's increasing magnification till you get to that blue square here. What you can see is that it gets kind of into the stratum corneum, kind of between the cell layers, but it does not, they were not able to find any nanoparticles in the cells. And so basically, there's no particle uptake into the cells if you do your assay with a 3D skin model. And I mean, of course, no exposure basically in that context means no risk, right? So it's not surprising that you're not seeing an effect here with these nanoparticles in these models. So I think with that, I'm coming to the summary here. I think what I tried to show was the skin models are considering the main route of exposure from cosmetics as well as the skin-specific metabolic fate. We believe we have successfully validated these two assays and find a very good predictive capacity. So overall sensitivity of 89% and specificity of 79%. The assays are actually in the meantime offered commercially under GLP at several labs, several CROs. We have tested 19 fragrance ingredients that really align to 100% with in vivo data. And I showed you a case study to kind of showcase the relevance of the exposure route in terms of dermal uptake as well. And again, I mean, OECD has approved OECD guidelines, but we cannot really start working on these OECD guidelines before, and that's a fairly new OECD rule, before a formal validation peer review has been performed. And that has to be done by a regulatory agency, and that is currently ongoing at ECVAM, or I shouldn't say ongoing, because ECVAM currently does not have a validation peer review committee. I think they're just going to advertise for people to apply for a new committee, which is hopefully forming later this year. So it'll be a while until OECD guidelines will be out there. But so I mean, it'll be a very long process and overall. And I yeah, of course, I'm happy that we got that far, but of course also it took quite a long time, and I hope it doesn't take again 15 years until we have an OECD guideline in our hands. With that, I want to acknowledge a lot of people, and I'm sure I forgot a lot, like the group of the Cosmetic Zero Task Force, the many collaborators that contributed to the data, as well as external experts that have been contributing to the work. So, of course, it would not have been possible to do this without all these valuable contributions and help. And really appreciate your interest in the topic, and happy to answer any questions you may have. And I'll probably stop sharing for now.
Thank you, Dr. Stefan, for this wonderful presentation and to introduce and to present this advance in the 3D genotoxicity testing. So maybe Peixoto can help us if we have some questions in the chat, in the YouTube, because I'm not following.
Dr. Daniel Bruschi is collecting the questions from the from the panel, but I actually, if you don't mind, I have one or two questions for you that is very intriguing. Your work was really intriguing. And I kept thinking, where did I meet you before? And it was Japan, 2017. I've been to the Japanese meeting, the Environmental Society meeting, and you guys were meeting in the block, one block away from us. And because the presentation in that Japanese meeting was extensively in Japanese, I kind of run away from there, and I got myself through the other meeting, and I saw some of interesting discussions. And I do remember now sitting there through one of the presentations of the skin micronucleus assay, the reconstructed skin micronucleus assay. So it was neat to find out that we have been in close contact before. We just did not know each other. Yeah. Nice. But Stefan, I have been working with micronucleus due mainly because of the radioactive accident in Brazil. I don't know if you are familiar with that, but in the 80s we have a population exposure to ionizing radiation from cesium-137. And I have been caring for the genetic follow-up of that population so far. And I saw your since that time in Japan that I have been thinking about your assay. You currently do it in vitro, right? You do the test in vitro. Mm-hmm. Have you done any in vivo test to see if the cells in the skins that are exposed, if they hold the memory of that exposure, and it can be traced back to one of the markers, especially micronucleus?
No, but I mean there is a method out there that actually some of my former colleagues here were involved in for micronucleus testing in skin in vivo. So I can dig out that paper and send it to you if you like.
Thank you, I appreciate that.
And I mean, I think what you're thinking about is whether potentially the stem cells, the skin in the skin, might have some remaining damage from that exposure. Is that correct?
Yeah, that is correct, because as you know, the stem cells will hold some of that memory, and not all of them will actually advance in the development of the skin. They will remain, they will stay behind, and then eventually, with the turnover of that epithelium, they will come about, and they will eliminate the micronucleus for sure, because they will divide horizontally, and then by doing so, they would lose the marker. However, if you let me put that to you, when a person is exposed and gets in contact with the radionuclide like cesium, and we have some of those patients in our hands, they have what we call the acute radiation syndrome, and they develop some skin lesions. Most of those radio lesions will have to be replaced with autologous grafting, for example. And these autologous graftings are always becoming inflamed again. Inflammation takes part of that, and the vessels do not reconstruct well. And that region is always subject to new scars, new lesions, and I always got intrigued, because some of that reaction, even 30 years after the initial exposure, may be because of the nature of the cells that replenish that tissue locally. And when I see that assay, and I was wondering if by, getting a puncture from that region in the vicinity where the radio lesion originally was, and where the graft is now setting, if we could actually carry out to find out micronucleus or any other marker in that area due to their original exposure. Then we could measure the half-life between the time of the initial exposure and if that still remains visible so many years after that, because for sure the tissue still reacts from that initial exposure.
I mean, that certainly is worth a try. I mean, it's also in the context of these methods, I think probably when it comes to long-term effects, I think the chromosomal aberration assay is probably a little more sensitive towards, rare, like of long-term effects and memorizing these things, because I think because it shows rare exchanges and things like that. Mm-hmm. Because to see an increase in the micronucleus above the spontaneous rate, that would require many cells to be affected, right? Not just one or two. So that I don't. It's hard to say, obviously, before you have tried.
Yeah, we have done all the markers. Currently, we have been working with CNV and SNPs. Counting the variants in the blood of this, we still have some of the markers are still retained in the population that are exposed. Mm-hmm. But it was just an idea when you start talking about that, and I that was an area that I never tested. I never tested their skin, but for sure it's if you send me the paper, I would gladly read it. Thank you so much for that.
Happy to do that.
Yeah, thank you.
Okay. Dr. Stefan, we had first of all, thank you for your lecture. It's a pleasure to hear your talk. First of all, we had a late question here in the chat, so I will read that for you. Is there any relation between the chemicals that showed false positive results that explain the results? The relation, the chemical structure of them.
Yeah, I mean we have I think a better idea on the false negative side probably than in the false positive side. On the false positive side, I think it's probably the same drivers than there are for the 2D cultures and things like that are already well known. For example, oxidative stress can lead to indirect DNA damage and other measures as well. And that's what we are thinking. For example, when you looked at the data set I presented from the side of the fragrance work, there's a lot of longer chain aldehydes in there that are, you have to dose them quite high actually to see an effect. And but they are quite efficiently detoxified up to a certain level. But then when you overwhelm the defense mechanisms, then they become positive, right? And so it's also a question of, how sturdy or tolerant is your system, and that's sometimes the problem in the 2D culture, right? If you just have your cancer cell line and media and nothing else, then of course there's not much there that a reactive chemical can react to, which is quite different than an in vivo situation. And then sometimes just a small effect is sufficient to kind of overwhelm the defense systems that we have. And that I think is why the 2D models have a higher percentage of false positives than in vivo or than the standard, than these more higher tier tissue models.
All right, thank you. One question, main question. Here, taking account in the relationship that you showed on your first graphic, I think, regarding the Ames test with the need to make the micronuclei in reconstructed skin model for regulatory purpose. What are the criteria for considering a negative compound in the Ames test? we know that environmental analysis is considered the use of 5 different strains with negative results in the presence and absence of S9. Would be the same criteria for the cosmetics?
Right. I mean, it's just basically, it's the same. It will be the same criteria as per OECD guideline, right? You need a proper aims, which have 5 strains, and of course, testing in the presence and absence of S9, and up to the guideline required doses. So that would be all of that, right? And of course, in the context of a 2-test battery, I mean, but that would be a separate discussion. You can argue whether you could go with a reduced battery, because certain things that are that might be missed if you leave out, for example, TA102 or E. coli, which are supposed to capture things that are causing oxidative stress. They are well captured by the glastogenicity assays. So I think in the context of a 2-test battery, a 4-strain aims would be fine. But again, I mean, there will be a separate discussion. But that has been a topic of the last IWGT meeting as well. And there's, I think, 2 or 3 papers that came out of that effort of that Japan meeting. So in case people are interested, if you Google for IWGT and AIMS test, I'm pretty sure you will find those papers.
Oh, thank you so much. And one last question from my side. Here in Brazil, until recently, it was difficult. We were unable to buy commercially available skin models such as AppSkin. So many labs, we developed in-house models from the 3D skin models. What's your opinion regarding the validity of using these in-house models for research and regulatory purposes?
Yeah, I mean, that's pretty much a general question, right? Because that doesn't only apply for the skin. I think what has happened in the last years is that people are a bit more conscious in the context of making sure that a method is valid. And I don't think there's any problems with using an in-house model, but I think people would have to show that it works. So, and in that context, I think what a regulator, for example, would want to see is a certain minimum number of experiments that you have, that it really works for some of the validation compounds, that it has been validated against, and that you have established a kind of a historical database in like a background range. What is the control level that's normal? How much variability do you see? Is it reproducible, and so on? So I think it's these questions that probably you would want to answer before producing a data set for a paper or for a regulatory submission. So there's always some effort, unfortunately, but I mean, if the model is more, I mean, if the intent is to use it long term, then it might be well worthwhile doing that.
All right, thank you so much.
You're very welcome.
Then you're muted.
Sorry, we have more questions in the chat or not? No?
No.
So I have just one question. It's not strictly related to the 3D skin module, but I would like to know how you see the perspective of using these 3D models for regulatory proposal considering exposure. Because today you present about the 3D skin models, but we have other models that have been developed for genotoxicity, like the lung and the liver, and how you see all these models being incorporated in the regulatory strategies.
I mean, I think that will come with time, right? I think there is already. I mean, that was one reason why we were in touch with the SCCS. I mean, they're not a regulatory agency per se, but they do decide about the criteria of cosmetic ingredients and what data they want to see. And there the skin models are already accepted in a weight of evidence assessment. And I think other people are looking at this as well, but the regulation always lags behind the science, right? So it'll take some time. And of course, the formal validation of a method and eventually OECD guideline will really fuel its use. But I mean, there is an interest. I know that from the labs that are offering them commercially, they have done quite a few. So there is an interest already, and there's use for that, obviously. And I know it's not only for internal decision making. Also, I think they get submitted already to regulatory agencies. And even a pharma company recently published on the 3D skin model for a dermal ingredient as well. So, and I think the same would be true for other, right, for lung or for liver or for, but I mean, again, I think to be shown hopefully that in a validation type effort that they really work.
Okay, thank you.
There is one more question from the chat from Samara. She's asking Dr. Stefan, in the micronucleus assay, in this skin model, do they use fish probes to determine whether or not micronuclei have centromeres?
Not as a standard, but I mean that has also been done. There's a paper out showing that works for the skin models. So I mean, there's no reason why that couldn't be done. We have not included that as a standard protocol because I mean, again, the validation was very labor intense, so we didn't want to add that on because the bigger question was, is it able? I mean, we know it's capable of detecting antigens, like I think any other micronucleus assays are too. We didn't go to that degree and did labeling of the centromeres, but that has been done and it has been shown that it works for the skin.
Oh, thank you. I think that's all from here. I don't know if Peixoto or Daniela has any other questions.
I guess not. You have, Peixoto?
No, I do not, but it was really interesting. I was really happy to be part of this webinar today.
Okay.
Very much appreciate the interest and the invitation. So
thank you again to be here and to give these lectures and to have time to answer all the questions. So I guess we can close the section, yes?
Yeah, just before that, I would like to present you, Dr. Pfuhler, with the words of Dr. Daniel Bruschi, our organizer, thanking you again for your participation and to be available to come and spend the afternoon with us. And also in the name of the Genetic Society, we would like to thank you all for that, for the time and for your kindness. Thank you very much.
It was a pleasure. Really appreciate the invite. So hope to see you sometime soon again.
And again.
Hold on just a second. I think I just received one last question here. Let me try to translate as fast as I can. In relation on the analysis of photogenotoxicity, the substances that are topically applied, there's any protocols that are being discussing about that regarding photogenotoxicity and substances that are just topically applied on this skin?
I mean, in the context of, I'm not sure I fully understand. Is it in the context of what the protocol is to apply the substance, or was it?
As I understood, it's like photogenotoxicity, like when we need the light to have the genotoxicity appearing in the. We have the substance.
Photogenotoxicity.
Yes,
okay.
Yes, sorry.
Right. Sorry.
No problem.
sorry, also that's a good topic. So actually, we do have a project that we just started with the Institute of In Vitro Sciences in the US to establish a photo version of the skin micronucleus assay. So that is something we actually actively working on. But I can't. There's nothing I can share yet, other that we have so far only looked at what the ideal UV strengths and so on is to work. But I mean, I don't have any results to share yet. Nobody has worked on it yet, to my knowledge. But I mean, we started working on it, so hopefully I'll be able to share something about that assay in the next year or so at one of the conferences or in a paper. So stay tuned.
One final question. We should let you go, but it's quite interesting. Have you tried anti-mutagenicity tests? So if you treat and then you treat again with something or prior to or whatever, just to be sure that your assay can also detect the anti-mutagenicity of products.
Ich rufe dich sofort zurück. Ja, sofort. All right, sorry. There was an urgent call. So let me. I mean, I have not looked at that really, so it's not something I'm really very familiar with, to be honest.
Okay, thank you.
So thank you, Stefan, again. And today we close this section, and we hope to have you here in person in the future. And thank you again for having your time to be here and give the lecture.
Thank you very much. And you all have a great rest of your day and hope to see you.
Okay, bye-bye.
Bye, everyone.
Bye-bye.
Bye-bye.
Parou a transmissão.